Hey there. In about a week or so, me and David was supposed to present this at GDC live. That is way easier than doing it this way. But we got some great content there that we wanted to share with you, so we're doing it this way instead. Um, to complicate things even further, I'm based out of Sweden. David is based out of London. So we're going to do this in two different locations and see how that comes along. So what are we going to talk about? Well, we're going to be looking at how Simplygon and Substance can be used together to create automatic optimization workflows where materials and optimized assets can be separated from each other. I'm first going to give you an introduction to Simplygon 9. After that, David is going to give you an overview of Substance. And after that, he's going to show some work he's done where Substance and Simplygon has been working together to create some pretty cool stuff, let's say. So who are we? Well, I'm Samuel, been in the games industry for about 20 years now, working with Simplygon as a evangelist, product expert. David would have presented himself given normal circumstances, but I'll take the honors here. David has an abundance of experience working in game tools, and now he's working with Adobe in the 3D and immersive special projects team. And actually, David and me was colleagues a while ago, and now we're presenting together again. So I'm going to start by giving you the latest news about Simplygon, and more specifically about Simplygon 9 that is going to be released shortly. Simplygon's focus is always automation. We want to empower technical artists with tools to create automatic optimization pipelines. And our goal is to do so without having to require heavy integration work. And Simplygon 9 has a lot of features and work going into this goal. When we look at building Simplygon, we have a very simple razor. We look at features, we consider, can this feature be part of an automatic workflow? If so, build it. If not, don't. Quite easy. And what is an automatic workflow? How do we see it? Well, we see that there's four pillars to an automatic optimization workflow. It has to be accessible, meaning that it has to be where you need it, given the environments you work in. It has to produce quality output so that you don't have to do touch-up work afterwards. The toolset needs to be broad enough to cover most of your needs so that you don't have to have different solutions or own solutions for certain parts. And it needs to be performant enough so that you can build all your assets in a nightly build if you'd like to reprocess everything. With Simplygon 9, we're tackling these four pillars. First, we are adding new integration options by adding APIs that allows you to hook into environments where Simplygon has been harder to access previously. We have sped up the turnaround time through an extensive infrastructure overhaul and also just core optimizations that makes the core algorithms faster. We've added new tools that specifically to support kit bashing workflows. We see that that's a very common way of working, and those assets have some problems that we can help out with. And lastly, we've improved quality by adding a new version of the remesher and also done some significant improvement to the reducer. Let's look at the first pillar here, accessibility. So we are adding a Python API, which is basically the same thing as the C++ API that has existed around, but which means that you can traverse from Python to C++ or vice versa quite easily. It makes Simplygon accessible in Max, Maya, Houdini, Blender, or for example, standalone Python, or if you're using Python integrated into your game engine, you should easily be able to integrate Simplygon there. We also have native integrations with Max, Maya, and UE4. And finally, we have a C++ a C# API that makes Simplygon accessible in Unity. When it comes to performance, we've done some heavy lifting and just plain optimizations on our core algorithms, where you'll see up to 25% faster processing times in the core. When it comes to Max and Maya, we rewrote the plugins completely, which means that the integrations go straight to the core API. For some assets, you see even up to 10 times faster processing times. And finally, we're changing how we distribute things, which means that with Simplygon 9, you're going to be able to hook into existing infrastructures, such as IncrediBuild or FastBuild. Well, we also provide you with a very simple distribution infrastructure if you'd like to use that instead. When it comes to quality, we have three things that we want to show here. First one is Remeasure version 2. The key difference between this remeasure and the previous one is that it's way better at finding holes, filling these out, which means that we can have higher quality at lower poly counts because we're not generating any interior geometry, which means that all the exterior geometry or the texture space can be consumed on the exterior of the object. Then we've worked a lot on shiny object loading, basically ensuring that there's as little changes as possible when you have specular areas like flat surfaces. Small differences in normal might cause big pops. We worked hard on reducing these. And finally, we also added volumetric culling, whereas we previously only had visibility-based culling. This one is more precise and comes in handy for the next feature I'm going to show you. And that is a kit bashing workflow support. We are building a feature we call Hollow Shell, and this feature is going to be exposed in UE4 through a completely new workflow, and also accessible through our APIs like any other feature. And we're also adding geometry data casters, which is a lot of what David has been using in his work, and he's going to talk more about what that is. But let's start with the kit bashing workflows. Problems with kit bashing assets, or kit bashed assets, is that you have a lot of hidden geometry in these. Since you just throwing objects together, it's easy to have a lot of geometry that you'll never expose to the player. This causes overdraw issues. If you're using light maps, it's quite easy to get a lot of light map space that's not actually visible. You get internal shadowing calculations that are costly. And finally, you get a high instance count, which can affect draw calls depending on how you do static batching and so on. So if we look at this video here, this is an example of a kit bashed asset where you got a bunch of rocks, pieces thrown together. And if you scrutinize this thoroughly, you'll see that there's a lot of internal geometry that will be costly from a performance point of view. Up to Simplygon 8.3, you've been able to tackle these kind of assets with reduction. Now, to be honest, it doesn't help that much, but sure, I mean, you could do a log chain for it. You can do aggregation and material merging, which will reduce the number of draw calls, but it costs texture space. And remeshing has also been an option, but typically more useful for far away representation of these kind of assets. With Simplygon 9, we're adding two features. We're adding hollow shell and clipped hollow shell. And if we look at this video, you'll see a rapid overview of these. So here's just a reduction, taking away 50%. Here's a hollow shell where it's merged together. And if we look at the see-through here, you can see that a lot of the internal geometry has been taken away. Then hollow shell, you can merge the materials if you can afford a texture space. So now it's just one draw call and a lot of the hidden geometry is taken away. Still, remeshing is also an option for faraway use, which if you want the really heavy reductions. And here are the materials produced by that. But if this scene is part of a bigger scene, for example, a rock face, you might generate a clipped hollow shell, which takes away everything that's not visible from the outside. So to reiterate, for kit bashed assets, we have reduction, helps with poly count, but it adds geometry data. Aggregation helps with instance count since it merges everything up. Also, draw calls naturally comes as an effect of that, but you have to pay geometry data and texture data. Remeshing helps with a lot of the problems of kit bashed assets, but it's typically not usable really close to the player, and it costs geometry data and texture data. Hollow shell comes in between here. It helps with all these things that remeshing does, but you don't have to pay with texture data. You can if you want to reduce the draw calls even further, but you can just generate a new geometry which is really optimal for the purpose. And clipped hollow shell helps with the same things, but reduces the poly count even further, thus reducing all of these categories even more. So next thing we added is geometry data casters. And if you look at it like this, it might look a bit odd, but what it actually is, these are different maps that produces output that you can use if you want to put materials on a proxy after the creation. So we can cast tangent space normals, material maps into texture maps that you can then use if you want to do something in runtime, for example. And we have a case that actually done that. So turn 10 had this case. Their problem was that they needed to optimize their cars heavily. When far away from a player, they needed to be able to draw it in one draw call. And since cars could be customized by the player, you couldn't just generate any possible permutation of this. You need to be able to modify it in runtime. So what is that they generated a mapping texture that they could use in the runtime to basically produce these kind of assets that can be customized in runtime. And actually, this is a really good point for me to hand over to David, because he's going to talk more about what this is and in more detail how you can do it yourself. So with that being said, I'm going to pass it on to David.
Thank you, Samuel. So I'm going to talk about the proof of concept I built using Substance and Simplygon. And now that there is a Python API in Simplygon 9, we can do some exciting things. So let's first talk a little bit about Substance. So Substance is a set of tools typically for building materials and applying materials and working with materials and assets. And one of the key thing here is the idea of a substance material. So a substance material is typically a procedural material that can also have some scan data, from which you can generate multiple different variations using these procedural parameters. And this image here is from the Substance Source archive, which is a great place to find good materials. And the way we output materials is basically by rendering out PBR texture maps. So with PBR, I mean like your typical base color, normal map, roughness, metalness, whatever you're using in your pipeline. And these images are then fed into the renderer and being consumed there in order to produce, pretty images such as the ones here in the image on the slide. So these materials are typically built in Substance Designer. Substance Designer is a node-based compositing 2D compositing engine that has a lot of features for making materials, but it can also be used for any type of image processing. And in this proof of concept, I've built a lot of my processing using Substance Designer, and it's a great way of building this type of workflow. I also want to mention Substance Automation Toolkit that is also being heavily used in this pipeline. So it's basically Python and batch tools for working with substance nodes and substance materials in a scripted fashion. So it allows you to render out the maps for a specific permutation of a substance material, and it allows you to automate your texturing. It allows you to manage your substance libraries and also integrate substance in various pipelines. So if you have a tool that doesn't support the substance archives natively, you can use it to render out the maps that are needed so they can be read by external applications, those type of things. So the problem statement I started from when we built this proof of concept was, obviously we want to start with creating lightweight models that downloads and render faster than the source materials, the source models. We also wanted server-side or late customization of materials. I didn't want to be locked into a set of predetermined permutations of materials. I wanted to be able to change materials when late in the pipeline. And so the point here is I wanted to make sure that all the material changes was done after the optimization. So if you change like a material color, you don't have to go through the optimization stage again. You can apply it directly on the optimized model from Simplygon. And the final part of it is I wanted to generally explore like what happens when you use substance materials with Simplygon. Does it work well? So some real world scenarios for problem statements such as those is one would be in video games where you want to want customizable content. So the example from turn 10 is an excellent one. Also e-commerce is an excellent example of where you want to be able to show lightweight models, but you want to have flexibility in the materials, ideally as far down the pipeline as possible. And it's also useful in general when you want faster iteration pipelines. If you just make material changes, you just want to update the textures. So here is a before and after shot or a model that came out of this pipeline. So on the left we have the original data. On the right you have the optimized one. And you can see they look very similar when you're zoomed out. If you zoom in, you can see a few small cracks in the facade. You can also see the texture resolution is lower on the optimized model. But for a web page, the right one is a very good substitution. And you can also see that the density of the mesh is significantly lower after the optimization. And we have also merged all the materials into a single atlas. So we use the remesher in Simplygon, which does a great job of taking all the material data, create a new atlas for it, and basically maps the original material data to the new model. So let's look at the processing pipeline that was used to create that model. So it has 4 stages: the data prep, optimization, material merging, and scene assembly. So the data prep is pretty much just taking the source model, in this case an OBJ file, and taking the source materials that are Substance archives. And what we do is we render out the maps for these Substance archives. So we get PBR maps. So these are the base color, normal, roughness, metalness type of maps. And we create a textured GLB file here. So this one goes into Simplygon for optimization, whereas these maps we're going to use in order to create textures for it. Next stage in the pipeline is optimization. So you take the source geometry, you optimize it and create the optimized geometry. We also create a set of utility maps. So these are the mesh maps that Samuel was talking about before. So for instance, here we have a UV to UV map. So that basically means in the UV space of the optimized geometry, we can figure out what is the UV coordinate on the source geometry for any point in this texture. And second one is a material ID map. So we can figure out what material is assigned to a specific part of the optimized model using the IDs from the source geometry. And in addition to that, we also have normals for the source geometry and tangents for the source geometry expressed in the UV of the optimized geometry, and the normals and tangents on the optimized geometry expressed in the UV for the optimized geometry. And what that allows us to do is transferring the normal map data from the tangent space normal maps applied to the source geometry to the tangent space of the optimized geometry. So next stage is material merging. So here we take the PBR match from the maps from the data prep stage and the utility maps from the optimization stage. And what we can do now is basically create atlases for the optimized geometry with the data from the PBR maps. And as you can see, it's only images going into this process, which means that we can easily build these workflows inside of Substance Designer. And what comes out are merged PBR maps. So it's basically the atlases for the optimized geometry with the material data from the high polygon model. The final stage is optimized scene assembly. And here we basically take the optimized scene and the merged PBR maps in order to create a textured optimized scene. And we basically use the GLTF writer from in the Simplygon SDK in order to assemble this final scene. So if you look at some data for this specific model, we started with 1.4 million triangles, 7 sets of textures. And with 7 sets of texture, it means that we have both the base color, normals, roughness, and metalness maps for all these 7 texture sets. And together, this is a 243 megabyte GLB file. The output is 11K triangles, 1 set of PBR maps, and a 14 megabyte GLB file. So this one is significantly lighter than the original model. So here you can see this process inside of Substance Designer. So in Designer, we only care about the low polygon geometry, the optimized geometry, because we're doing everything using images at this point. And so what we can do now is we can expand all the wires. So the thick green wires represent multiple textures. If we expand them, you can see there are tons of textures being wired here. And this node that we're looking at now is the one that basically has all the mesh maps that I was referring to before. And we also have off-the-shelf Substance materials here. These are from Substance Source. And as you can see, all these materials are live. So if we change the leather color, for instance, on this one, you can see it updates directly on the model. And in the 2D image on the left, you can see the atlases generated by the network in this processing. So you can see the base color map and the normal map and everything being generated by this graph. So I've made a few predefined assignments here. So we can going from the leather to the suede setup. So this is another configuration for this chair. And We can also use this fabric one here. And this one was actually created for a different model. So we can switch out the model here and then also switch out the mesh maps. And again, since this is a 2D compositing operation, we can apply it to a different model by just switching out those maps. And now we have a nice configuration for this other chair. And we can also apply some of the other ones to this chair, since there is a little bit smartness in how the materials are assigned. They're not like just assigned to an index, but they're assigned by a little bit of semantic information. So let's dig a little bit deeper. So we're going to look at the material merging process, how we dealt with the normal maps, and finally how we dealt with some aliasing that was showing up, causing the textures not looking as good as they could. So the material merging stage is where we take, the high polygon model with a bunch of materials assigned and make them into an atlas. So this is what we start from. We have various materials assigned to various parts of this model. And through the optimization, we create the material ID map and the UV remap map. And here you can see, so this is in the texture space of the optimized model. So at any point here, we can figure out what is the UV on the high polygon model and what is the material ID on the high polygon model. So using this data now, we can select the material based on the material ID, and then we can pick a specific UV based on the UV texture. And here again, we can get rid of the model because now it's all happening in texture space. We basically, for each pixel, look up material and UV coordinate and then sample the right texture for that. And we have to do that for all the maps that we're transferring. So this would include the base color, normals, roughness, and metalness in my pipeline. So another problem we have here is when you use tangent space normal maps for your materials, you have a difference in tangent space between the source model and the destination model. And in order for the tangent space normal map to apply correctly on the optimized model, we need to do a little bit of work. So basically the first step we do is we do all the UV transfer the way we used to do it, we did for all the other maps. And then for each pixel, we transform the normal from the tangent space normal map to world space using the normals from the high polygon model and the tangents from the high polygon models. So next step is going into another transformation where we basically take this world space normal and transfer it to the tangent space of the low polygon model using the tangent and the normal map from the low polygon model. So when I'm talking about these tangents and normal maps here, they're all representing the actual geometric normal, not the normal from the normal map. That one comes in as a separate source here. So the final thing I want to dig a little bit deeper in is the aliasing that shows up when you're having difference in texture resolution between the source materials and the destination materials. So in many cases, we have tiling materials on the high resolution models, and it basically means that if you don't think about this, you can end up with very noisy results. So on the left here, you can see we have done a transfer without considering aliasing and not doing MIP mapping, which happens to be the solution for this. And you can see there's all kind of noise, especially in the normal map on the left image. On the right image, we have a much smoother and better looking results because we dealt with it using MIP mapping. And the other thing I want to mention here is this is actually not only about visual fidelity, it's also about download size. So textures with a lot of noise in compress much worse than textures without noise, meaning that we could shave off some 20% of the texture data by doing proper texture filtering here. So here is the same problem shown in texture space, and you can see you have all this high frequency noise in the left image where we haven't done any MIP mapping, and on the right one it looks much smoother. So the way we solve this is using the same strategy as you do in an ordinary renderer. we use mip mapping. So this is an example when you're not using mip mapping. You can see there is a significant difference in the size between the pixel in the atlas compared to the pixel in the texture that we're sampling from. And what it means that it can take any random value from within the square on the right and put that in, and it shows up as noise. By pre-scaling the images and filtering them properly, we can now select the right resolution for the image on the in the source material, where we have filtered away the noise but preserved details that are relevant for that scale, and we transfer from that one, and we get a significantly better result. So in order to wrap this up, this is a proof of concept that can work as inspiration. We hope we can make it available to you sometime soon. It's also an example of how the Simplygon and Substance APIs can work together. And I'm sure you have similar situations in your pipeline if you're using both Substance and Simplygon. And we would love to hear about your challenges and thoughts about this. And our emails are in the lower right corner of this slide. So don't be shy, send us an email if you have any questions or thoughts, and we'll be happy to talk to you about it.
Yeah, how did that go?
Yeah, that was an interesting experience. Hope we can see each other in person next time we have a shared presentation.
That would be awesome. Well, I'm back at least. Just wanted to say hi and goodbye. And thank you for listening.
Yeah, thank you so much for listening. And yeah, don't forget to get in touch with us if you have any questions or thoughts.
No, I mean, we'd love to hear your thoughts. That's how we build things. So, thanks.
Thank you all.
Bye-bye.